Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Rosemary Pike with us today. Hello, Rosemary.
Hi, it's great to be here.
Well,
Uh,
thank you so much for agreeing to talk about your very awesome article, which we will get to here shortly. And it is July 24th of 2025 as we record this. And Rosemary, what's your geolocation? Where are you at?
so I am at the center, the Harvard Smithsonian Center for Astrophysics,
Okay.
in Boston, Massachusetts.
Uh-huh. And do we have a little humid summer weather going on the East Coast?
It's pretty hot. It's a good heat wave. It's supposed to get up to the mid 90s today. So
Oh, that would be like air conditioning for me. So I'm in Phoenix and, we will regularly hit the 110s without issue. So 90 feels so nice.
it is very humid though.
Yeah, classic. But on the other hand, I don't know, most people know, but in Phoenix is June, July, August is the wet season in Phoenix. That's when we get our monsoons and other weather phenomena. So yeah, it's the humidity's up a little bit in Phoenix, but we tell them it's a dry heat anyway. It's a dry heat. You won't notice it. Very good. And Rosemary, what do you like to do for research?
So I work at the Minor Planet Center uh,
Cool.
here at CFA.
Uh-huh.
So as part of that, I do a lot of support work for minor bodies. So we catalog all of the observations that people send us of different moving objects in the solar system. So any small bodies,
Very
so
cool.
near Earth asteroids, comets, trans-Neptunian objects, natural satellites, so distant satellites of planets. And my research interest specifically is the most distant component of that group. So the trans-Neptunian objects out beyond Neptune, these
Uh-huh.
icy remnants of the planetary formation scattered in the distant solar system.
Very nice. Very nice. Great topic. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. LiDO, discovery of a 10 to 1 resonator with a novel libration state. And Rosemary, take us away.
Yeah, thanks. So this work has been a major effort and as part of a wider survey that I'm doing with quite a few collaborators. So it's an international collaboration. We have people in the US, also Canada, Taiwan, and we're working together using the Canada, France, Hawaii telescope to discover trans-Neptunian objects.
Nice.
And that's what the LiDO survey is. So it's the Large Inclination Distant Objects Survey.
Hmm.
So when we designed the survey, we were thinking we needed to look off the ecliptic plane to find objects that come to pericenter at a better location.
Okay.
Sorry, yeah. So most TNOs are most discoverable on the ecliptic plane, where they're brightest. But a lot of them actually are high inclination, and so they're off that plane. And they spend most of their time off the plane, but they do come through the plane. So a lot of these ecliptic surveys over time have found a lot of TNOs
Cool. Very cool.
that are high inclination, but we're actually looking um, for these higher inclination objects, which are easier to find if you look off ecliptic.
I'm with you. Cool.
We put in the CFHT proposal under Samantha Lawler and Charles Chen, and they're the survey PIs.
Cool.
And we've found some really interesting objects. So just as a sort of brief introduction, there are lots of mean motion resonances of Neptune that are very populated with objects.
Hmm.
And these large populations were placed into these mean motion resonances as a result of giant planet migration and sculpting of a group of small bodies, some of which may have been in the current area of the Trans-Neptunian belt, and some
Ah,
of which were scattered out. When
yeah.
you get all the way out to the 10 to 1, these are most likely scattered things. There's not like a cold expected to be a cold belt that formed in that location.
Right.
Yeah. Yeah, so we have all this planetary migration of the giant planets that sculpts the outer solar system and leaves signatures in the trans-Neptunian object region. So we're trying to measure the signatures of migration in the populations of trans-Neptunian objects and in the
Mhm.
orbits. that we see. So
Cool.
in particular, we find these N-to-1 resonators. And so this resonance is very efficient at capturing things.
Okay.
Uh, so we tend to refer to this as sticky.
Yeah. Okay. I was going to ask that what's a resonance sticking, but there you go. Okay.
Yeah. So it's if particles get scattered, the resonance is a bit wide and they tend to get caught in that resonance. And then they can spend a decent amount of time in the resonance, you know, mega years, sometimes a giga year. And then they wander out, they may stick in another resonance. And that's sort of what you have highlighted here is talking about how basically about 40% of the objects that are we would think of as scattering currently moving around the outer solar system are
Uh-huh.
actually temporarily sticking in resonance.
Okay.
Uh, and these are particularly common in the N-to-1 resonances, like the 3-to-1, 4-to-1,
Yes.
5-to-1, and the N-to-2 resonances. Although we do see it as well with much higher order resonances,
Okay.
but the lifetimes there are shorter.
Yes. Okay.
So then, of course, the further you get away from Neptune, you get like a slight decrease in sticking. And so one of the things, we've been wondering is sort of how far out is this sticking significant such that
Yeah.
we're finding these populations.
Cool. I'm with you.
So one of the um, yeah, so it's also important when we find an object in a distant end-to-one resonator, in a distant end-to-one resonance, one of the big things we're looking for is this long-term stable or is this sticking?
Yeah.
Because you have sort of two different kind of stuck populations. You have
Okay.
the ones that were scattered in the era of giant planet migration,
Uh-huh.
got put in a really stable orbit like 4 billion years ago.
Hmm.
They're still there. But then you also have sort of the currently scattering objects. And so one of the big questions we ask when we find things are these primordial,
Right.
or are they the result of the giant planet migration, or are they something that could be produced in our current known solar system architecture?
Aha. Okay. I'm with you.
Yeah. So finding basically these objects is a lot harder because they're on average much further away, but they
Hmm.
do, as resonant objects, come in reasonably close to Neptune's orbit. So they may have a pericenter of something like 37 to 45.
Okay.
And so we see a small fraction of them when they're much closer to pericenter.
Nice. That makes them easier. Hmm.
And so previous ecliptic surveys have been biased to
Oh,
finding low inclination objects. And this is important for these distant resonators
okay.
because the energy imparted in the planetary scattering
Yeah.
pumps up their E, it also pumps up their inclination.
Yes.
And so on average, they are much hotter in inclination than all of the sort of
Okay.
classical Kuiper belt objects, even the hot ones,
Right.
sort of in the 42 to 47 AU range.
Okay. Good. Cool.
So ecliptic surveys have found similar objects to these, including like OSIS and CFEPS, and the DES also found a similar object. So you
Hmm.
do find some, but it's harder. They're harder to find on the ecliptic plane, and so we looked off the ecliptic plane. The LiDO survey looked at a range of higher inclinations to find things.
Cool. Okay. I'm with you.
So here, yeah, we're just talking about all the different biases that go into basically what your survey is likely to find.
Yes.
Um,
Okay.
and so one of the important things about trying to sort of predict where we'll find objects is
Here we go.
we use sort of like toy models of the different resonances.
Hmm.
So for an N-to-1 resonance, we typically assume there's a symmetric island, and then two asymmetric islands, and these constrain where the pericenter is relative to Neptune. So
Yes.
um, you can actually have pretty high libration in the symmetric islands, but still you're restricted in where the objects come to pericenter with respect to Neptune. And for a very long time, we've been designing TNO discovery surveys based on assuming, the pericenter is always away from Neptune.
Okay. I'm with you.
Uh,
Hmm.
And particularly the asymmetric islands have pretty small libration, and you can predict pretty accurately where those are going to be.
Mm,
But one of the things we'll talk about later is that it turns out at very high inclination, these assumptions are no longer particularly appropriate.
cool. Okay. I'm with you.
So here, we're saying, basically that this simple model is not sufficient at high inclination. Basically, because what we see additionally is basically the symmetric island shifting to librate around zero instead of 180 degrees away from Neptune.
Ew, ew. Okay.
That
That is interesting.
essentially means that some of these objects would come to pericenter in the direction of Neptune, but off the plane.
Yes. Yes. Hmm. Very unusual.
That's not where we've been looking for them. And so
Right.
that's kind of an important
Yeah.
basically thing that we've learned from here is basically we should be thinking a little more broadly about how we search for resonant objects and what our observation biases are.
Very cool. Very cool. Okay.
So this is a let's see. Yeah, so this is a bit of an introduction to the survey, which was LiDO, the Large Inclination Distant Objects Survey. And we're working on the main survey paper now, and hopefully it will be out soon.
Very
Um,
good.
we used a pretty similar discovery and tracking system to the Outer Solar System Origin Survey,
Yep.
in that we used the Canada, France, Hawaii telescope, and we used triplets for object discovery. So there are two main directions one can take.
Yes.
You can use a series of images spaced out in time, or you can use shift and stack. So here we're using a set of three, basically trying to go as deep as we possibly can with CFHT. So our limiting magnitude was somewhere between 25 to 25.6 in the wideband filter.
Uh-huh.
And so this is pretty much the limit of what you can do with about a 4 meter in individual images. You can get deeper with stacking. But here we were trying to go sort of as deep as possible with a triplet set. And we're
Hmm.
trying to find these fainter objects, particularly because these are the kinds of things that, say, LSST is not going to be sensitive to because their limiting magnitude will be brighter.
Okay. Okay.
They'll
Hmm.
have a much larger area and a shallower depth.
Yes.
And area and depth can be, both can be used to increase your number of detections, and then they find slightly different things. And as we were interested in, say, finding distant things,
Faintly.
um, we were particularly interested in increased depth over increased area.
Okay.
Um,
Fair enough.
the characterized sample in LiDO is 125 objects. We found 141 objects, and the difference there is basically the ones that were fainter than 25.0 to 25.6
Okay.
in whichever block they were in. So we don't refer to those objects as characterized because we cannot quantify the detection efficiency,
Okay.
high accuracy there. So we don't know if, say, finding one object is representative of 10 intrinsic objects or 1,000.
Yeah.
Um, so we don't consider those object characterized. So we don't, say, use them to try to determine a population estimate.
There
They
you
can
go.
still be very interesting.
Oh yeah.
Um, there's a 5-to-1 and a 7-to-1 resonator in our uncharacterized sample,
Wow.
which many qualities with this 10-to-1 that we're discussing here.
Yeah. Very cool.
Um, but they're not characterized, which is part of why we were looking at this object first, because it is part of the characterized sample.
Nice. Good example here of BN40.
Yeah, so 2020 VN40. This is the 10-to-1 object. So we discovered it in the main LiDO survey. And the survey was designed to discover and track objects for over like a 2 to 3 year arc. Um,
Hmm.
we were primarily searching for high inclination Plutinos when we designed the survey.
Okay.
So that track time was tailored to be sufficient for classifying things in the 3-to-2 Neptune resonance,
Okay.
with semi-major axes of about 39 AU, not semi-major axes over, 100 AU.
Yes.
So we did not have a long enough arc length to say whether the object was conclusively in the 10-to-1 resonance,
Okay. Hmm.
which we often measure as is quoted here in the delta A over A. So that's the uncertainty in the semi-major axis over the semi-major axis. So it
Yeah.
wasn't sufficiently good. Um, and if we look at the Poincare map in figure one
Yeah. Good.
with just the LiDO data, the uncertainty bars actually extended out of the region of resonance.
Okay. Hmm.
How we determine this is one way to think about whether an object is resonant. So you can see the resonant angle in an n-to-1. The resonant angle is
Hmm.
instead of psi, it's simplifies to phi versus a semi-major axis, and you can see the two on the two sides. You see the different
Okay.
asymmetric islands, and then the symmetric island goes around the outer edge,
Got it. The
and
whole,
we have our real object shown on there in black.
yes. Very cool. Okay.
So
Uh,
before we did additional astrometry, that's where the object was. In it was much bigger. So it spanned about 140.5 to a little bit lower. So we were looking at maybe like
uh-huh.
50% of the uncertainty being within the 10 to 1. And we thought, this is interesting. This could be a 10 to 1 resonator. We need additional data,
Good.
as one always does.
Of
Uh,
course. Cool.
so so we went to Gemini Observatory and I've requested director's time to get some more observations of this object. And they awarded us some time that we used to get some additional tracking.
Yes.
Yeah, which was great. And then
Very
with that
cool.
additional tracking, we had a precise enough orbit that we were actually able to pull out some very low signal noise detections from some archival Subaru data.
Okay. Mhm.
That increased our arc significantly again. And that is what brought down the uncertainty to what you see in this figure here.
Nice. Very cool. Okay. I'm with you.
Yeah. So the total arc length is over 2,000 days,
Mhm.
and our target, and we exceeded our target orbital uncertainty in the delta A over
Okay.
A. So our final barycentric orbit was a semi-major axis of 139.95.
Okay. Okay. Hmm. Yes.
So and it's not shown here, but the inclination is about 33 degrees. And so an object like this is
Okay.
much more difficult to find on an ecliptic survey. And we're looking
Oh,
at a centricity of about zero point 0.7.
okay.
It's also coming in relatively close. So while this has a very large semi-major axis, it was not discovered at a particularly large distance.
Right.
So, but uh, it is the largest semi-major axis confirmed resonant object at this time. So
Hmm.
another possible 10 to 1, and then we have 23 to 2 in OSIS that are like likely resonators
Wow.
that are slightly farther out. But to the best of my knowledge, this is the largest semi-major axis um, conclusively classified resonator.
Cool. Congratulations. Very nice. Okay.
Yeah, so I jumped ahead a little bit, so I think we can jump back to um the resonant classification.
Uh-huh.
Um, so the previous section is just about the additional astrometric data that we talked about. And then here
Yep.
we looked at the point Carré map, and then we also did a bunch of simulations. Um, so Cat Volk is the one who generated the point Carré map that we were looking at.
Very nice.
Same method that she does for a lot of her other previous work.
Hmm. Okay. Yes.
Yeah.
Yeah.
And then
Yeah.
based on that, we thought it was most likely to be resonant, but we wanted to look at the behavior over time,
Yes.
over a variety of clones.
Wow.
So
Okay.
we
Miracle
we
clones.
generate a lot of orbits. So I think I'm in the next paragraph actually
Okay.
here. So we want to generate a whole lot of orbits that are consistent mathematically with all the astrometry that we started with. For TNOs, basically the uncertainty is reasonably well represented with a Gaussian.
Yeah.
And so
Sigma.
for each astrometric measurement, we take the expected uncertainty, and then we resample those, and then we redo an orbital fit.
Yes.
And so
Mhm.
this produces a range of orbital fits that are all consistent with each other. Um, and and then that gives us sort of a list of starting clones. So we took our nominal clone and then 200 additional clones, and we did n-body simulations to see how those behaved over sort of 30 megayear timescales and then over gig year timescales as well.
Yes.
So we used rebound with WH fast for the
Uh-huh.
integration
There's a,
and the sun and the four giant planets. Um,
yep, rebound. Maybe
yep.
let's take a look at figure two, maybe, because we're kind of
Yeah, I think so. So
dancing
we can
around
jump to
it.
figure two here.
Yeah.
If anyone who's interested in all the numbers for the rebound input can look at the text later. Um, and yeah, so this is sort of a visual representation of all the test particles that we started with. So you can see
Uh-huh.
when we generated these orbits, most of them cluster in A and E and I. So if we look at just the bottom two panels to start,
Mm.
you can see the range of A and then
Yeah.
the interdependence between A and E as well for the orbit fitting,
Oh,
and
definitely. Okay.
the inclination.
Okay.
And so the color coding here is telling you the duration of the first period of resonance.
Okay.
So you can see the lighter they are, the longer they're resonant. And here, the first period of resonance is basically, if we look at them over time, um, it starts out resonant, and when does it stop being resonant? And so we're
Fair
just
enough.
measuring
Okay.
that time.
Mm-hmm.
So to clarify, almost all of these, they stop being resonant, and then they become resonant again, and then they stop again, and then they become resonant again. So
Uh,
it's not meant to be representative of sort of the fraction of time that they spend in resonance. It's just the period of first resonance.
okay.
But
I'm
we
with
can
you.
get an idea of sort of how stable each particle is at its particular initial conditions from looking at a plot like this. So
Yes.
firstly, you'll notice there are two objects that are not resonant at time zero.
These are these black squares.
Two black squares, yeah.
Uh-huh. Yep.
They're about three-ish sigma outliers, um,
Yeah.
and the largest, pretty much the largest semi-major axis things. And they both also show some resonant behavior, just not at time zero.
Okay.
And we also see that sort
Ah.
of the slightly lower semi-major axis things, those tend to be like higher stability lifetimes.
Okay. Yes, because they are a lighter color up here.
Yeah.
Okay. I am.
Yeah.
Patience.
But we
Good
should
job, but
consider when
yeah.
we think about particles like this, we should consider any of them to be a reasonable representation of what the object could be doing over time.
Yes.
And then the top plot there, I'm showing the libration center. So we talked a bit about the Poincaré Islands.
Yes.
So we're looking at the leading island right there is where most of the particles are. So that would be
Yes.
uh, like the left ball in the Poincaré map.
Mm-hmm.
And then we're looking at some that are symmetric, that are like higher up in that plot there, and you're not seeing anything in the trailing island.
Interesting.
So the star represents the nominal clone there, which is what we get without doing any orbital fuzzing. And
Ah,
sometimes
okay.
the nominal clone is very well behaved, like in this case, and sometimes you'll see everything sort of shifting relative to the nominal, which might indicate an issue in your astrometry or might just indicate something interesting
Hmm.
about the space that the object is actually in.
Yes. Yes. Okay.
So
Very good. I'm with you.
these are our starting test particles, and we integrated them for 1 gig a year to see what they would
Okay.
do.
Okay. Mhm. Just an example we
Yeah,
got.
so this is an
Yep. For
example.
30 million years.
This is the nominal clone here over 30 meg years. Because we'll look at a gig year later and everything sort of smushes together. So it's nice to look at it in
Early.
30 mega years. This is what we would typically consider a classification timescale for TINOs. So here you've got a long enough timescale to see sort of how things are evolving, whether or not things are resonant. You can see,
Cool.
whether things are cycling or circulating.
Yes. Yeah.
And
Uh,
you can see the interesting behavior in the semi-major axis. So
uh,
the blue regions denote areas that the classification code we use has determined the object is resonant.
okay.
So what it's doing to do that determination is it's looking at the resonant angle, which is phi on the bottom panel there. Uh,
Yes. Hmm.
and it's looking for confinement of that angle. And it's using a variation on a windowing method.
Ah.
So
Okay.
basically, it's looking for empty holes on the plot that it thinks are because it's not hitting. So if you look at sort of the very tail end on the bottom right there,
Hmm.
right around 30 mega years, you can see the object is circulating there. It's not in resonance. And so that's basically what we don't want to flag those. We want to find the places where it's resonant. And
Yes.
then the tighter confined ones, those are the asymmetric islands. So you can see it starts in the leading island and it jumps to the trailing asymmetric island.
Okay.
And after that, it goes into the symmetric island. Uh,
Cool.
it's not stable in any of these particular islands. And so, for the most part, for a lot of these, the fraction in particular islands for these distant resonances is probably not indicative of anything primordial. They're all sort of slipping between these different configurations.
Island hopping. Hmm.
Yeah. So you can see it's also labeling what it's calculating as the extent of the resonance, and then the center. And so the center is indicated by those red lines,
Right. Hmm.
and then the particular island, and then the particular window extent, which we would call the amplitude,
Yes.
it's showing in blue. So you can
Yes.
see there are a couple of places where it transitions where it's okay, but not excellent. And that can result in a little bit of blurring in some of the plots that we see later. But basically, for each window, we measure whether it's resonant or not, what the
Yep.
center libration center is, and the libration amplitude. And then these are sort of the bulk properties of each clone that we consider when we try to understand the evolution of the object as a whole.
I'm with you.
Yeah. So this looks like what we expected when we looked at it. This
Yeah.
30 integration looks like a 10 to 1 resonator. It's resonant more than half the time,
Okay.
at which point we would typically call it a resonator. There's certainly different thresholds you can apply for stronger, less sticky resonances. You might want to apply a higher threshold, something like
Okay.
3 to
Hmm.
2. But yeah, but this is pretty appropriate for the 10 to 1. Um, so yeah, this is what we're seeing over the first 30 mega years. Um,
Hmm.
that most of the clones are pretty resonant, just like this nominal.
Nice. Okay. Good.
So
I'm with you.
then we ran 1 gigayear simulations
Right.
because one of the things, like I mentioned earlier, we were most interested in is could this object be primordial, or could this object have basically been scattered out during the era of giant planet migration, or did it come to be here later, right? So is it sort of a currently unstable object that's
Yep.
just scattering around,
Along the
or
line.
could this be a signature of basically giant planet scattering?
Okay. Hmm.
So that's when we try to look at a lot of the bulk statistics of the particles here. So it can start with the bottom left one here, the time of scattering. So basically, this is the point at which the average semi-major axis was significantly different from the resonant semi-major axis in
Okay.
the. So we're basically looking for when the particle leaves the resonance.
Moves on
So
top.
none of the particles left the resonance in 30 mega years, which is, like I said, the classical
Oh,
time scale.
yes. Right.
That's where we basically say, all right, these are all resonant or resonant interacting particles.
With you.
Um,
Hmm.
but you can see about half the particles leave around zero point 0.7
Point 0.7.
years.
Yeah. Hmm.
Yeah. And then you know,
Wow.
more than 60% of the particles leave by a gig
A gig
year.
a year.
And
They're
so
out
so we
disintegrating.
don't think that this is a long-term stable particle, or represents a long ago
Uh-huh.
implantation,
Yeah.
because it's unlikely that it would have survived 4 gigayears until now.
Okay.
Um,
How
so
about that?
this looks like a scattering sticking object.
Yes. Yes.
Um,
And
So then the rest of these,
uh,
if you go up, the first one sort of
uh-huh.
is just a
Yes.
different representation of the color plot, right?
Yes.
So it's um, the first one and the one below it. So the period of first resonance is what's in the plot. So that's that one. That's how
Yes.
long they're resonant the first time they're resonant. Then the top one is how long they're resonant in one island. So if you remember the
Right.
nominal clone, it actually jumps islands a few times before it's
Yes.
not resonant.
Yes.
Um, those two are subtly different, but basically show, relatively long periods of first resonance. Um,
Yeah, it hangs out for a while. 50%. Let's see. 50 is about 10. A few times 10 is 6. Few million. Few million. Okay.
and then if we look at the first 30 mega years on the top right there, you can see the
Uh-huh.
fraction of time that the particles are resonant. So 50% of the particles are resonant like 70% of the time,
Yeah.
65%,
Uh-huh.
like
Uh-huh.
that, right? More than 60% of the time. Um,
Interesting.
so it looks like on average, the particle is most likely resonant. But if we look at a gigayear, 50% of the particles are only resonant about 30% of the time, because a
Yes.
lot of them scatter. And so
Yes.
that sort of supports the idea that this is not a long-term, gig-year stable particle. It's kind of a mega-year
Hmm.
stable resonant
And we'll
integrator.
call it quasi-stable on million
Yeah.
year time scales. Hmm.
Yeah. And then if on the bottom right in the different colors, that's just the fraction of time broken down by the different islands. And so here you'll see the first appearance of libration around 0 degrees from
Ah,
one of these plots here. You can
interesting.
see all the islands we expected. 180 is the symmetric, and
Yes.
then the 90 and 270 are the asymmetric. And then we
Mhm.
have this libration around 0, which you'll see, does actually happen for about, 40, 50% of the clones,
Okay.
some amount of time. Um,
Interesting. Zero. Okay.
yeah. So,
It's novel.
so yeah. So when we saw this, we decided to follow up because we
Yeah.
didn't expect to see it.
Right.
Um, so I think
Hmm.
let's skip the next plot and go to figure 6.
Okay.
Talk to look at it first.
Okay. Let's go to figure six. And here we go. Eye hole behavior.
Yeah. So this is one of the test particles over a gigayear instead of 30 megayears.
I'm with
Um,
you.
we
Hmm.
saw when we first saw these plots, we thought we were looking at some sort of very weird beating. So
Wow.
we increased our right frequency significantly and did it again
Uh-huh. Uh-huh.
until we were sampling, 50 to 100 points on every oscillation,
Yep.
and it was super clear. We were seeing libration around 0. Uh,
Wow.
so you see it in the 5 panel there with those like blue gaps in the middle.
Yes.
Uh, so it's also moving between libration around 0 and libration around 180.
Yes.
And we see this pattern. This pattern was consistent for basically
Okay.
the time that we saw
Okay.
it with different clones. So there are a few things we noticed right away when we saw this, and a few of and some of the other particles where this was a really significant component
Okay.
of their behavior, is that the inclination got higher and the eccentricity got lower.
Indeed, it grows. Amplitude gets
Yeah.
a little bigger.
So there's
Eccentricity dropping.
Yeah.
That's
So there's likely
interesting.
a critical inclination for this to happen.
Ooh.
But it's probably also likely a critical combination of E and I.
Yeah.
Um, and so we're not one of our future work ideas is to kind of try to track down how one would measure the critical values sort of needed to achieve this type of migration, this type of
Island hopping. Or
migration. So
yes.
yeah.
Very cool. Very
Yeah. So
back to that. Okay.
yeah, so now we can go back. So we wanted to see whether this like change in E and I, this restricted range of E and I, was
Mhm.
typical of all our clones in general.
Okay.
And
Okay.
so we plotted them up as figure 5. And for
Hmm.
each of these, each point here represents a single blue line, a single blue window.
Yes.
So
From
every time,
yes.
yeah, a single one
Uh-huh.
of those little blue lines. So
Uh-huh.
every window for
Yes.
which the particle was resonant in that window, we
Yes.
put 1 point on each of these plots. And
Okay.
so we put in the resonant libration center on the bottom. So that's,
Hmm.
0 to 360.
Yes.
But then we put the semi-major axis, and these are averaged over the window. Semi-major.
Yes. Okay.
So you see sort of what you expect right in the middle. There's a lot of particles in the symmetric island
Yes.
centered on 180.
180. Yes.
You also see two clear islands around 90 and 270 that are the asymmetric islands.
I'm with you.
And you can
Uh-huh.
see a little bit of blurring between them, which is like I said, it's just
Yeah.
particles are moving between them, and so you catch them sort of your averages
In transit.
if
Uh-huh.
they're in transit between the islands. But you
I'm
also see this really clear feature around 0
indeed.
at both larger I and lower E within the simulation. And so this is
Yes.
seen
Yes.
in a lot of particles.
Interesting. Cool.
So we have this cool vibration around 0
Mm-hmm.
in a bunch of the simulations.
Mm-hmm. Nice. Okay.
Yeah. So we wanted to try to see, why this could be happening.
Yes. Hmm.
So,
Talk.
so we looked at a bunch of different Hamiltonians,
Yes.
sort of exploring the phase space.
Yes.
And I think let's jump to figure 7.
Okay. So we're gonna do some Hamiltonian popping around.
Yeah, so if you would like to read
Come on,
those
moment,
story Hamiltonians in your free time after watching the video,
and then derive them.
they're all here. Um, and
Very good. Oh, yes, these look like. There
So
you go.
here we go. Okay, so here we're looking on the top panel at just the same particle phi. And you can see the transition between the libration around zero to the symmetric to libration around zero to symmetric back and forth repeatedly.
Oh, very nice. Yes, yes,
Um,
yes, yes.
and Ruth Marie Clay did a lot of work on this
Okay.
with me as well, and she made these plots here, and she linked it to the change in omega or argument of parity.
That's
So here you can see
that's
that when omega is zero,
okay.
so the argument of perihelion is zero, so perihelion is close to the plane. You're
Yes.
getting close to the planetary plane. You're getting sort of the standard expected symmetric behavior. And then as omega precesses, you see a transitional behavior where it starts to slip. The island is basically slipping.
Oh,
And then at omega of 90, it has popped into this libration around zero here.
very cool. Okay. Huh. Wow.
Yeah. And
Wow.
so if you go down a little bit, you can see these curves superimposed on the Hamiltonian. All
Hmm.
these curves are sort of the same energy, so you can see it's actually
Oh,
less
yes.
stable once it's in the libration around zero. But basically, you see the sort of normal islands just like we expect them, and
Uh-huh.
then you see them start to distort, and then they actually slide. So if you look at this with more steps, they slide over, and it basically the symmetric island pops to go
Yes.
the other way. Uh,
Yes. Interesting. Huh. Okay,
yeah,
and just to be clear here, the colors of each of these W's correspond to these. Okay.
yes, they correspond to the level curves on each of those. Yeah.
Right.
So
Right.
we're looking at the at those three cases, basically the Hamiltonian in those three particular cases.
Okay.
Yeah.
Nice.
So this behavior appears to be cyclical,
Yes.
but relatively stable. This going back and forth between these different phases. Uh,
Hmm.
yeah, is relatively stable, and
Yeah, I'll
probably
go to.
requires a reasonably large inclination, which is why we haven't seen it in, say, real objects in the solar system previously.
Yeah, stable out to at least a gig a year. Hmm. Very nice. I gotcha. I'm with you.
Yeah.
Okay.
So we are referring this to this as eye hole libration because you see the little like holes in the plot in the middle.
Yes, yes, yes. Eye hole. Love it. Okay.
Yeah. So we have a bit of a visualization in figure 8 to look at the 2-to-1 and kind of get an idea of basically
Ah,
how this works. So we remember these particles are very inclined relative to the plane.
yes.
Uh, and you can see the ascending node
Okay.
and
Ignis.
basically the color denotes the distance from Neptune as the object does multiple orbits.
Yes. Okay. Boop, boop. Yes. Yes. I'm with you here.
The left panel is showing an omega of 0 setup, and then the right panel is showing an omega of 90. And they're
Okay.
both inclination of 55-degree particles.
Okay.
So the
With you.
black dots are the initial location of conjunction with Neptune.
Okay.
The
Uh-huh.
connected red dots show the closest approach to Neptune or the orbit within that conjunction. So we're looking at sort of how close they get to Neptune and like the tugs that Neptune would exert as they
Okay.
get that close approach.
Okay. Good start. And we got the later conjunctions marked with the X's. Okay.
So
Gotcha.
the black X, yeah, indicates the later conjunction
Mhm.
after
Here you go around.
sort of like 10 resonant orbits later, um,
Hmm.
showing basically the perturbations of Neptune moving the conjunction and the resonant angle. sort of back and forth around zero.
Yes. Yes. Awesome.
So
That's a nice illustration.
yeah, so this behavior requires large inclination,
Mhm.
but of the particles, but one of the reasons um, we want to call attention to this sort of now is with LSST, there's going to be a lot of fields that are wide, broadly sky covered, as it's not designed just to find solar system things in the ecliptic. So we're going to start finding a lot more high
Good.
inclination objects.
Okay.
And when we look at those high inclination
Yeah.
objects, we need to consider that, they may be doing very unusual resonant behaviors. And if we use a simple classifier that say doesn't look for libration amplitude center slipping
Mhm.
or libration around zero, we might miss out on some of
Yeah.
these really interesting objects.
Mm-hmm. Mm-hmm. Very nice.
So
Yeah.
for the purposes of like this particular object, we've decided that we're classifying it as a scattering sticking TNO that is currently resonant in the 10 to 1.
Beautiful.
Um, And as such, we can't make any sort of unfortunately, big arguments about stability, about how it might have gotten there.
Yeah. Yeah.
So it's something that can be produced in our current solar system. But the fact that we found one and there's another likely one does mean there's probably a very large population of objects sticking in this resonance,
Mm-hmm.
all the way out to the 10 to 1. Uh,
Very,
so
very cool. And I'll give a little shout out to open source code here, SB Check
yes.
that out.
Yeah, so that is Cat classification code. And it does not it's a machine learning code
Yes.
that does not look at the resonant angle first as a diagnostic of resonance.
Cool.
So it is
Good.
looking for those there's patterns in the semi-major axis, for example. There's a
Huh?
whole list of criteria, but it looks at sort of measurable quantifiables out of simulations in order to assign a probability of resonance.
Uh-huh.
Um, and we've been testing it on some of these high I objects out of the Large Inclination Distant Objects Survey.
Mm-hmm.
And it's been very accurate at pulling out some of our very unusual objects.
Nice. Good.
In particular, some of the mixed mode resonators that we've been finding in the survey,
Uh,
as well as the N-to-1 resonators, which we struggled with a windowing method to get a high enough accuracy. It's pulling these out really well. So,
yes.
so highly recommend taking a look at that code if you're doing resonant classification. Um, so yeah, it is available.
Nice. Very cool. Very cool. Rosemary, I want to thank you so much for walking us through your very awesome article. Beautiful. Very good. And let's see, you mentioned it a couple of times as we went through, and a little bit more toward the end there. So let me push on it a little bit and ask, where do you think we go from here, given the published article? You mentioned that there are 141 of these things in your sample. We only talked about one of them being
We did
40.
talk about one of
So
them,
are
yeah.
there other ones?
There are other interesting ones for sure.
Okay,
So the
okay.
next step is definitely um, there's some theoretical work we need to do to understand basically how this works in a more theoretical way.
Okay.
So we are planning to do a follow-up theory paper to better understand basically how this is, how this actually functions.
Right.
Whether basically there's some speculation in the paper and whether we can define, say, a critical angle. And so,
Oh,
or
yeah,
sorry,
yeah.
critical inclination.
Right.
So that's going to be something we're looking at in a follow-up paper. We may also include some of the data from the 5 to 1 and 7 to 1 that I mentioned in that
Okay.
paper.
Mhm.
Um,
Sure.
I believe it's the 5 to 1 in particular actually shows this behavior at the start of the simulations, unlike the 10 to 1,
Oh,
where it's something that is happening sort of later in the particle integration history. So yeah, we're definitely going to follow up on those. We also have some other kind of interesting stuff. In LiDO, there are a couple of mixed mode resonators where there's an inclination component to the resonant term as well.
nice. Cool. Wonder how that happens. Okay.
Yeah, so basically there's if we think about the phi equation has additional terms in it.
Hmm. Right.
That so basically But there haven't been very many of those in the solar system in general, and really not many because it basically requires very high particle inclination for the strength of those resonances to be
Yes.
meaningful compared to the pure E resonances.
Okay.
So there are a couple of those that we're looking at, sort of exploring now, which modes we're seeing and how large the size of that resonance is. And then, of course, the survey was also designed to find the plutinos.
Yes.
Um, Found a lot of plutinos, and we are working on both the 3 to 2 and 5 to 2 resonances. Um, as compared to a survey like AAS, it had about
Yeah.
um,
Uh-huh.
four times the area, but was almost purely ecliptic. And if you look at the OSIS objects at the same inclination range as ours, it's
Yes.
almost the same number of objects.
Okay.
So we're sort of doubling this characterized high I sample, and so we can better constrain sort of the wings of the inclination distribution in all of these different resonances where we found objects.
Mm-hmm.
Those are kind of the next steps for the LiDO survey, and we're now at a really exciting place because we have all of our detections, we have our categorization, and so we're ready to do some modeling. So
So this one's sort of a teaser. This is a pretty rich vein, right? So it'll be really nice to see this develop over the next couple of years as we investigate these high I resonators. Very cool.
yeah,
Very nice. Rosemary, I want to thank you once again for walking us through your very awesome article. Thank you.
thank you.
And that'll do, everyone. And I hope this made your Resonator Astronomy Day just a little bit better. And we will see you on the next one. Bye bye.